extra credit.
Right. Okay, so my plan is to just go through these questions that are on the midterm 2 review session problems, and then see how people are feeling after that. I do have more problems besides just these that actually I haven't shown anybody yet. So we could be here a long time if we want to be, but let me try and hit all the highlights once at least, and then come back and repeat things a second time if I need to. All of this material kind of ties together, so we're reviewing a lot of the material with any one given problem. So let's just start off kind of easy here. Number 1, and I don't know if you've all printed these out, but if you haven't, I'll write down the questions anyway. This says, find a spanning set for the null space of this matrix here. 1, 2, 0, -2, 3, and -4, -8, 0, 8, -12. Okay? So this is a 2x5 matrix, and the null space is a subspace. Keep in mind, if something is not a subspace, then you can't find a spanning set, you can't find a basis, you can't find a dimension, you can't do any of that stuff, right, if it's not a subspace. By the way, the null space of this matrix would be a subspace of what? Of what vector space?
2x5 matrices. 2x5. R5.
Oh? What's that?
R5.
R5. R5 is in. Remember, this is a 2x5 matrix. The null space is a subspace of Rn. The row space is a subspace of Rn. And the column space is a subspace of Rm. Okay, so there's an M and an N here. So M is 2 and N is 5. So when I'm talking about the null space, it's a subspace of R5. And part of the reason you know that is because you're looking for vectors that are going to be killed by this matrix when you do the matrix multiplication. And if you're doing a matrix multiplication and you've got 5 slots across here, you have to have 5 slots down here for it to even make sense to do those dot products. So even if you don't have it memorized, whether it's M or N in which position, you can always figure it out again by just realizing that the number of columns here is the number of slots you're going to need over here. And that's what N represents. Okay? So, so we're finding a spanning set for this subspace of R5. So does anybody have a suggestion how we do this?
Row echelon form?
Put it into row echelon form. Very good. So let's take this matrix and put it into row echelon form. I'm going to try not to dwell on EROs too much tonight. By the way, a lot of the time, we don't really need a full-blown row echelon form. We just need to know how many pivots and which columns have pivots that we're going to end up with. So that's one thing to keep in mind. In this case, I'll go ahead and just work it out because it's only one step, really. I'm just going to add the first row to the second row with a multiple of 4. So that would give me a 0 here. The whole point is to try to get a 0 right here. Okay, if I put a 4 there, then I'm going to, actually, it looks like the whole thing's going to 0 out, doesn't it?
Yes.
Okay, good. So, by the way, you can also just wipe something off with a line through it. I'll know that that means it's all zeroed out. Okay, saves you a little bit of time. All right, so this is my row echelon form like that. Okay, so what do I need to do next?
Back substitute.
Okay, back substitute, and of course, there's really variables. This is one thing that, notice in the question, they don't really write down any unknowns in this system of equations. So it's up to you guys to kind of decide what variables you want to use. What variables would you like to use here?
R, S, T.
I don't want to use R, S, and T because those are my free variables that I always use. What are the typical variables that we would use for a system? X, Y, Z, then we run out of letters, right? So we just get this lex that can go backwards to W and V. Something like that. Okay. So that's just fine. It doesn't actually matter what you call these things, right? That actually doesn't matter. Okay, so back substitution, of course, there's really no back substitution to do because there's only one equation here. the point is that all of these variables are free. Right? Now if you want, you can reassign them and say, all right, v is equal to t, w is equal to s, z is equal to r, and I don't know, y is equal to q, or something like that. And then you'd have to express x in terms of those 4 variables, but you may as well just use these letters. So if you do that, then you can solve for x. So from the first equation here, basically you're going to move all of the other variables to the other side. So it'll be negative 2y plus 2w minus 3v. That's solving for x here. I mean, really there's an equation here, x plus 2y minus 2w plus 3v equals 0. And if you solve for x, this is what you get. So your null space, just put it here, the null space of A is the set. So it's a set of vectors, so I have to use my squiggly little braces here. And I just start putting down my variables, so I have negative 2y plus 2w minus 3v, comma, and then y, comma, z, comma, w, comma, v. So these last 4 slots are just the free variables, right? And it's only the first slot that's being expressed in terms of those free variables. And then this will be such that y, z, w, v are elements of the real numbers. Okay? That's what the null space of A actually is. Of course, that's not a spanning set for it. So once I know how my set looks, my whole set, how do I obtain a spanning set?
Bust out the variables.
Good, bust out the variables. I can't imagine that that won't come up. So you got to be able to bust out the variables. We do it quite often to find a spanning set here. So if I bust out, so now we're basically going to, we can actually go straight to the spanning set, I believe. You guys are going to have to tell me if I'm going too fast here. But basically to get the spanning set, what I do is I pull my variables out one at a time. So if I pull out the y, variable, then there's a negative 2 in the first slot associated with it. In the second slot there's a 1. And then in slots 3, 4, and 5 we have 0. Agreed? Okay, and then when I pull out the z, well, the only place I have a z is in the middle slot, so that's a 0, 0, 1, 0, 0. Notice I'm getting vectors in R5. That's what I expected. It's a subspace of R5. My third one is going to be the w variable. When I pull the w out, when I bust it out, I'll have a 2 in the first slot. And then there's nothing here, 1 here, and 0 here. So 0, 0, 1, 0. Okay, everybody with me? Okay, and then the last one is the v. And I have negative 3 in the first slot, and then 3 zeros in a row, and then a 1 at the end. And then we just make that into a set, and we've got it. Okay? That's a fairly easy little warm-up question. We didn't really have to do much work in terms of the EROs. Rest assured, guys, if you make a mistake on the EROs, but you give me an answer that is compatible with what your result was, so if you screw this thing up somehow with the row operations and your pivots aren't in the right places, but then you write down the answer based on your matrix, I won't penalize you for that answer if it's consistent with your matrix. On the other hand, if you have the wrong matrix and somehow you have the right answer, then I won't be very happy. See, I don't care that much about the answer. I care about knowing that you have the process right. So don't give up on a problem just because the EROs seem wrong. Aaron?
So we know that there's 5 components in the column?
Yeah.
Because it's an Rn, correct?
Right.
Okay.
Yeah.
Now, that doesn't necessarily mean there's 5 vectors, though.
No, because this is only a subspace of R5. So R5 is 5-dimensional, but if I want to span something smaller than all of R5, I may not need 5 vectors. In fact, here we only need 4 vectors. Right? So so by the way, what is the dimension of the null space of A? It's 4. 1, 2, 3, 4. Right? And what is the nullity of this matrix?
1. No, 4. 4.
The dimension of the null space is 4. Okay, the nullity is 4. What's the rank of the matrix?
1.
1. There's only one pivot. So 1 plus 4,
It's 5.
right, adds up to 5, which is n, which is the number of columns, right? So that's the rank nullity theorem. Okay, so it's just another example of that. Okay, makes sense? Yeah, go ahead, Curtis.
So why was the z vector 0, 0, 1, 0, 0 when z is 0?
Z is not equal to 0.
Okay.
Oh, that reminds me, on this, oh man, did I fool a lot of people. I wasn't trying to. On this take-home redo quiz, I gave you this matrix, 0, 3, 1, 0, negative 6, 2, negative 2, and 0, 12, 4. This is probably the #1 mistake on the whole take-home quiz from the whole class, which is find a basis for the null space. So people row reduced it, and they got, of course, they got basically, that's the row reduced form. So everybody said that z was free, and then everybody solved for y, which was fine. But then here was the mistake. Everybody said, oh, this column of x's is 0, so x is 0. And of course, that is not true, right? This is actually going back to the first midterm. The point is the x doesn't appear in the equations anywhere, right? There is no equation. This first equation is 3y plus z equals 0. The second equation is negative 6y minus 2z equals 0. And the third equation is 12y plus 4z equals 0. There's no mention of x anywhere in that system. So that doesn't mean that x is 0. That actually means that x is free. No matter what number x is equal to, you won't contradict the solutions to this system, right? So getting a 0 in a particular column doesn't mean that that variable is 0. It actually means quite the opposite. It means that it's actually totally free to be any number it wants to be. Good point. I'm glad you brought that up, because that's something a lot of people had some issues with. Okay, anything else on that example? This is kind of a warm-up problem, kind of get us going here a little bit. Okay, let's do another example. I'm just going to kind of go down my sheet in order here for now. So number 2, I'm going to give you a set of vectors, 2 minus x squared, 1 plus x squared, and 3 minus x. And what I want to know is, you know what, I'm just going to rephrase the question. I just want to know, is it Li, does it span V, is it both, or is it neither? Let's just go through. Oh, and what is V? V is P2 of R. So there's my vector space, P2 of R. And my question is just, do these vectors, are they Li only, span V only, both, or neither? So we're going to circle the right answer and then justify it. For every one of these types of problems, if you know some basic information, you can cross off 2 of the 4 choices immediately. Right? What's the basic information we sort of need to know?
K and N.
Yeah, the K and the N. The N is the dimension of the vector space. So and of course you guys need to know, this kind of goes without saying, you need to know the dimensions of the basic vector spaces like Rn, Pn, M by N matrices, right? Those are standard examples. So what is the dimension of P2 of R?
3.
3, very good. So N is 3. And how many vectors did I give you?
3.
3. Okay, so K is equal to N in this case. 3 vectors in a 3-dimensional space. So that's the right number of vectors. It doesn't automatically mean that it's a good set of vectors, though. Right? So, but what can we cross off? These two, right? It's either going to be a win-win or a loss-loss, basically. They're either, it's either thumbs up or thumbs down on this one. Okay. So how do you decide which way to go here?
Put the matrix
C1 plus.
Go ahead, Brandon.
Put the vectors into a matrix and then do the
And how do you put them into a matrix?
columns.
Okay, and so would this be good? 2, 0, negative x squared, Does this look good?
No.
No, this is not what you want to do. I see a lot of people do this, try and do something like that. Your matrix should never have x's in it, or it should never have polynomials in it. Actually, what you really want to have are just the coefficients, right? So the 2 is the constant term, there is no x term, and there's a -1 in front of the x squared term. And then for the middle vector, 1 plus x squared, you're just going to get 1, 1, 1. And on the third one, you're going to get 3, -1, and 0. Now, the way I've arranged it here, I put the constants on the top row, the x terms on the middle row, and the x squared term on the bottom row. You don't have to do that. You could choose to put this bottom row on top and this row on the bottom or something. Of course, that's just an ERO exchange of rows, which doesn't really matter anyway. Yeah, go ahead, Sergio.
You're not going to want us to prove the definition of linear independence?
Okay, so that's a good question. So is it okay to just jump to here, right? On this kind of problem that's very computational and procedural problem, it is okay to just jump to here. Okay. There was a question on the review packet though where you're kind of forced into knowing the definition of linear independence to be able to solve it because I was dealing with abstract vectors. If I give you a problem with abstract vectors, it's very hard to solve it using a matrix because you don't know what to put into the matrix. But here, it's pretty simple to do that. What Sergio is asking me, and it's fine if you want to be more clear, and just say, well, C1 times 2 minus x squared. See, this is really the starting point for testing your vectors for linear independence, is something like this, right? You assume that there is a linear combination of your vectors that cancels out. And then what you realize is that this polynomial equation is actually 3 equations. There's a constant term equation, there's an x term equation, and there's an x squared term equation. So 3 equations, and those 3 equations end up here. So for example, the constant term, there's 2c1 plus c2 plus 3c3, right? That has to be 0. That's the first line. That's the equation.
So
on
even
the
if we
first
go
line.
through that process, we're still going to end up...
You're going to end up here.
Okay.
You're going to end up here. So what I'm saying is, if you want to jump straight to here because you know that's what's going to happen, I'm okay with that. All right. It's just that if I don't give you vectors that you can sink your teeth into, like these vectors here, and it's something more abstract, then you may... I do want you to know the definition of linear independence. Yeah, Aaron?
So either way, you would have to put the C1 and C2s together, and then you would come up with a matrix that looks like that.
Right. Well, you put all the constant terms together, and then there's all of the x terms. There is no x term there. Here, there's c2x and minus c3x. So c2 minus c. So c2. I should write this on another line actually. So c2 minus c3 has to equal 0 as well, right? Which is the second line. And then the x squared term is going to give you the bottom line. Making sense? Okay, so in this case we just have to take the determinant of this thing. Maybe I can, for this determinant you can just use the 3x3 arrow method. I'm not going to be, I won't ask you any question on this test that I could have asked you on the last test, in the sense that I'm not going to ask you to do some horrific determinant where you have to remember things like a 4x4 determinant with the cofactor expansion. That was the first test, so we have enough to think about right now with this stuff. So don't worry about that. But a 3x3 should be able to do it, right? It's just by the arrow method. So in my notes, it turns out that the determinant of this is not 0. That's all you need to know, is if it's 0 or not. If the determinant is not 0, then what do we conclude?
It's invertible.
It's invertible, and
Both Li and F.
right, that's a good thing. You tend to think of this as a good thing, right? It's both linearly independent and it's a spanning set. Okay, so this implies both. If the determinant was equal to 0, then it would be neither, right? You would have linear dependencies, and the dimension of what these things span would be less than all of P2 of R, right? So they kind of go hand in hand. Okay, we all right on that part? Okay. Guess I'll come back over here, do the next one. When you're doing these EROs, does it matter if you get a row of zeros? Is that really an important thing to keep track of?
No.
Not so much. What's more important?
Consistency.
The columns, and specifically what about them?
Number of nodes.
Where how many pivots and where they're at. That's exactly right. The pivots are the key to everything. Always the pivots. So that's what you want to look for. Okay, let's go on. Let's do problem 3. Oh, this is a topic people are struggling with. I think have struggled with. Maybe we're getting it down a little bit better now. Subspaces. Okay, guys, I've said it many times. I'll say it again. It's better to write too much than not enough. And too many people are not writing enough words. Just kind of variables appear out of the sky, and I don't know what they mean, right? I can't read your mind, and I'm not going to necessarily assume because you wrote something down that it's exactly what I think you might have meant, right? So please take the guessing game out of it for me. It'll make my grading experience a lot easier. The way you take the guessing out of it is you write it down. You just put it into words. Write a sentence down. I know it's a math class. It doesn't seem like you have to write a lot of words. We do need some words here for this. Okay, so here's the first one. We're going to take the vector space of 2 by 3 matrices, so M2, 3 of R, or 2 by 3, either way. And then S is going to be the set of matrices capital A in the M2, 3 of R, such that the rows of A sum to 1. And the question is asking you to show that it's a subspace or explain why it's not a subspace. So it's kind of a thumbs up, thumbs down question, right? It's a yes/no question. And it would be really helpful. You want to get to the point of comfort with this material that you can think, without writing a lot down, you can think ahead as to what the answer is. So you know which way to route your solution. So just mentally thinking about it is an okay thing to do. You don't have to just start diving into, oh, I've got to check all these things, right? First thing to do is just give yourself permission to just kind of calmly think about this set. And what are some of the things that you should be thinking about first? The zero vector, right? If the zero vector is in there. So in this case, the zero vector, of course, we need to know what the zero vector is. The zero vector would be this matrix, right? It's a 2 by 3 matrix like that. So is that matrix in the set S?
No.
No, this is not in S, right? So that implies what? What does that tell you already?
It's not a subspace.
S is not a subspace, exactly. S is not a subspace.
Because the 1 is a fixed number, so it'll never be 0.
If this is any number other than 1, it's not going to work. I'm sorry, any number other than 0.
It's like,
Yeah,
what?
that. Any number other than 0, it's not going to work. Right? Okay, so it's not a subspace, so we're done. If it was in the set, does that mean it is a subspace?
No.
No, then we have to do more work, right, to think about it. So let's actually get to that case. That's part B. So this is the second part here. Part B is the same exact thing, except S is going to be the set of A, element of M2 by 3 of R, such that the rows of A sum to 0. Okay? Try that. So again, we have to think about whether it's a thumbs up or thumbs down. What's your opinion this time?
S is a 0 vector.
Maybe.
It maybe is a subspace, because this time if you put down the 0 matrix, well, the rows of that, if you add the rows of the first row adds up to 0, the second row adds up to 0, so both rows add up to 0. So this is an element of S. It doesn't hurt to write that down. I mean, you're not gonna get a substantial amount of partial credit for that, because it's only one little piece of the whole solution, but it is something, just to let me know that you knew that that was a test that you should do. So you check for the zero vector, and it is in the set, so that just basically means we have to keep going, right? We have to keep working at it. Okay, so what do you think then? I mean, before we start writing anything down, do you think this will be a subspace?
Yes.
Yes.
Okay, so what are the ingredients of it being a subspace?
Closure under addition.
All in unison. You guys have this stuff down. Yeah, closure under addition and closure under scalar multiplication. Exactly. So you just have to mentally think for a minute. If you take two different matrices, but the rows of each matrix add up to 0, then if you added those two together, would you get another matrix whose rows added up to 0?
Yes.
Yeah, you would. It's just basically, adding 6 numbers, the first 3 of which add up to 0, and the second 3 of which add up to 0. So all 6 of them are going to add up to 0. And you do that on each row. See, that's a thought process. You don't have to write all that down, right, on your solution, but that's a good thought process to just at least give yourself confidence that you actually are proving the right thing, that it is a subspace. Then we can start trying to write it down, which is what we're going to do here in a more formal way. Okay? Everybody good so far on this? Let's give it a shot. So closure under addition. How do you want me to start that? Go ahead, Gabby.
Let A be a vector and then do each one.
Okay, so A is going to be a vector in the set?
Yeah.
Okay, so it's in the set, so it's a 2 by 3 matrix whose rows add up to 0, right? So does it work to do something like this? Or that doesn't work. Would that be a good way to start?
No.
Guys, if you're proving that something is true, that it is closed under addition, doing one specific example is not going to convince me of it. That's the whole thing where I kept talking about Saturdays are sunny. All Saturdays are sunny, and just because one Saturday is sunny doesn't mean they all are. So you don't want to do a specific example. So what would my generic example? So if I don't want to do a specific, how do I do it so that it'll look arbitrary?
A and B and then like E.
Okay, so would this be a good way to do it?
No.
You could do that. You could do that, but you would then be forced into adding a proviso at the end of it, where you'd have to say A plus B plus C is 0 and D plus E plus F is 0. And you'd have this extra baggage you'd have to carry along the whole solution. So there's actually a better way, or I think an easier way, does anybody know what I'm thinking of?
AB minus A minus.
Change the C, and we've done these in the group work, by the way. We've done some very similar examples. Just change the last entry to be what it needs to be so that the rows will add up to 0. The point is that the first 2 entries in each row are arbitrary. And it's just the last one that has to be rigged to cancel out. So the negative of A plus B and the negative of B plus E. I don't know if that's going to get out of my way or not. That's okay though. You guys can see that. Okay, so there's my first matrix. Okay, is that all I need?
You need a second one.
And I need another one, we can call it capital B. Same form. Do we use the same letters again though?
No.
No, because this matrix may or may not be the same matrix. So what I suggest you do is just get some totally different letters in there. So I'd probably use something like X and Y and negative of X plus Y. You can choose to do subscripts. I can have like A1s and B1s and then A2s and B2s. I'm finding that I think it's better not to do that. It's just better to just get some totally different letters. So down here we'll have Z and W, and then negative of Z plus W, something like that. So these are 2 general looking elements of S, right? So we should also say that here, be in S. So let them be in S. Okay, so we got that. So then what?
Add them together.
Add them together for closure under addition. So we add them together. Now that's just a basic